Welcome to Hononegah High School. I'm Brian Brown, and today we'll be taking a look at using the n-a=s method to draw molecules. And while this has its limitations for first-year chemistry students, it does one really important thing. It helps us find the number of bonds, and that can make it significantly easier to draw molecules when you're starting to learn to draw them. So what we're going to look at is how we draw molecules. Now, for simple molecules, we'll be using the n-a=s method, and we'll end up drawing what we call Lewis dot structures. So we're going to end up with structures that end up looking like this. And the key to drawing molecules is to find the number of bonds, because that's often where students struggle. And the method we use is right up front. I'm going to show you how many bonds you've got. Now, if it follows the octet rule, so first thing you'd have to do when you do this is ask yourself if it follows the octet rule. But if it follows the octet rule, this method, n-a=s, is an easy way to find your number of bonds. First thing we're going to do is we're going to determine the number of bonds right up front then. And remember, a bond is a shared electron pair. So every bond really is two electrons being shared. And we're going to use the following formula, n-a=s. N stands for the total number of electrons needed for all to have a full octet. So basically, we call it the octet rule because everything needs 8, except for hydrogen, which only needs 2, because hydrogen's nearest noble gas, which would be the stable electron configuration, only has 2 electrons. So basically, when we do N, what we're doing is counting up how many 8s and how many 2s do we have. So this general formula I put right here is in essence what you're going to use every single time. We're always going to use that method for finding your N, because we have hydrogens that need 2 and everything else needs 8. So when you look at your molecule, SO3 in this case, how many non-hydrogens do we have? Well, we've got 1 sulfur and we have 3 oxygens for a total of 4 atoms. So we have 4 atoms that need 8. We have no hydrogens, so 0 atoms that need 2. So we've got 4 8s and 0 2s. Well, 4 times 8 is 32, plus 0 would still be 32. So in SO3, we need a total of 32 electrons for all of the sulfur and all of the oxygen atoms to be stable. So that's our N. How many total electrons do we need for everything to be stable? A stands for available electrons. So it's the total number of valence of electrons. And this is something we've been doing many, many chapters now, is looking on the periodic table. And remember, in the S&P block, we can just count across everything in the first column as 1, everything in the second column as 2. Then we get to the P block. It's got the 2s electrons, and that first P column would have 3 total because the 2 s's and the 1 p. So just count across the S&P block 1 to 8. So everything in the hydrogen column has 1, beryllium column has 2, boron column has 3, carbon column has 4, and so on. So you're really just counting across the periodic table. Now, that's how you determine your A. So what would that look like? Well, for SO3, we've got a sulfur. If you look at where it's at on the periodic table, it's in the 5th column over in the S&P block. So our sulfur, it's in the 6th column over in the S&P block. So our sulfur has 6 valence electrons. And then oxygen, well, that's in the same column. So it also has 6. And we have 3 different oxygens in that substance for a total of 24. So the sulfur gives us 6, each oxygen gives us 6. That's a total of 24 available. So we needed 32, but we only have 24 electrons available. So we have to share some electrons to get everything a full octet. Now, one thing to add here that I'm going to come back to later, if we have a polyatomic ion rather than a neutral molecule, that means we've changed the number of valence electrons, or the number of available electrons in the substance. So the quick, easy way to determine how many electrons we have available when we have a charge is determine your A, just like this, and then subtract the charge. Because a negative charge means we have extra electrons. Subtracting a negative gives us a positive. So if we determine the A value is 5, but we have a -1 charge, 5 minus -1 is 6. That's actually how many electrons I have available. So remember, when you have charge, we have to fix our A by subtracting the charge. Now, the next thing would be S. S stands for how many electrons are being shared. Well, if we need 32, we only have 24. 32 minus 24 means we have 8 electrons that need to be shared in order for everything to have a full octet. Well, a bond is a pair of electrons being shared. Remember, we talked about that up here. A shared electron pair is a bond. So every 2 electrons that have to be shared would be 1 bond. So all we really have to do to get the number of bonds is take our number of shared electrons and divide by 2. So in the case of SO3, 8 divided by 2 would be 4. So SO3 has to have 4 bonds. So in this particular method, the very first thing we're going to do is determine how many bonds we've got, which is really powerful for making drawing a lot easier, especially when we have double and triple bonds. Next thing we're going to do is we're going to draw our molecule without bonds. Now, first we're going to draw the central atom. Now, it is usually the one there's only one of, so this takes care of almost every case you're ever going to see. CH4, there's one C, 4 H's, C's got to go in the middle. NH3, there's one N, 3 H's, N's got to go in the middle. So most of the time this is a no-brainer. But if you're not sure, remember you have an electronegativity table, the least electronegative one will always be in the middle. And one thing you'll start noticing is you're never going to see a hydrogen in the middle because hydrogen, remember, it needs to form one bond and it's done. So it's never going to be in the middle. It's always going to be on the outside. And typically halogens are kind of in the same boat. Halogens are column 7, so they have 7 valence electrons. They need one more. So usually they form one bond and they're done. So you're never going to see hydrogen or fluorine or chlorine or bromine or iodine. Those things are typically not going to be in the middle. Hydrogen, never, ever, ever, ever. There are some weird things with halogens, but we're never going to see them in first year chemistry. So hydrogens and halogens, never put them in the middle. So really, the one there's only one of, put in the middle. If you're not sure, check electronegativities. The one with the lowest electronegativity, 100% of the time will go in the middle. And then you just draw your other atoms spaced out around it because they're going to be somewhere around that substance. Doesn't matter where you put them, just space them out. So if you had 3 Cl's and an F, doesn't matter where you put the F, just space it, the 3 Cl's and the F out around that central atom. So in the case of SO3, remember, we only have one S, so that means it's going to go in the middle. But if you're not sure, look up S's electronegativity, and you'll see it's less than O's. So we're going to put S in the middle, and we're just going to space the 3 O's out around it. Don't matter where you put them, just space them out. When we get into shapes, this spacing idea will help make our transition to understanding the shapes a little bit easier. Now, next thing we're going to do is everything's got to be connected to the center. Otherwise, we wouldn't have a molecule, it would be falling apart. So you're going to connect every outside atom to that central atom with a single bond because they all have to be at least single bonded to the central atom. Now, if you have extra ones left over, and here's where the N minus A equals S method is so useful. If we know up front we've got X number of bonds, it's always going to tell us when we have more bonds than we needed to put in all single bonds, and we're going to have double or triple bonds in there. So that's really the secret to this method, making this so much easier, is if you have leftover bonds from the total you were supposed to add, you're going to have double bonds. No, multiple bonds are typically going to go, and normally you're not going to have a choice here because it's all going to be equal where to put it, but there are certain restrictions. Remember, hydrogen is one and done. One bond and it's finished, so it's never going to get a multiple bond. Halogens, they are rarely ever going to get multiple bonds, never in your case, because they're going to be one and done as well. Once they form one bond, they've got their 8 electrons, they're finished as well. So typically you're going to see it going from a central atom like a carbon. And if you've got multiple carbons, it's just going to be going to the 2 carbons. So sometimes we can have multiple centers. We will eventually look at some of those in the chapter. But normally it's going to go to that central atom to the outside, typically to a B, N, or O. And usually, most of the time you're going to see this, it's going to an oxygen. Now, it's really not that big of a deal because it can't go 2 hydrogens. And really, if you look at what's left, you're going to have an equal choice about where to put it. So it's going to be, there's no choice left, so you put it whatever it says. So this is a lot less complicated than you really think. If you have a multiple bond, just don't put it to a hydrogen or a halogen. And you'll see that you never really have much of a choice. And if there is a choice, it's always equal, so it doesn't matter where you put it. So in the case of SO3, and you'll see that at work here, we had sulfur in the middle and our 3 oxygens spaced out around it. First, we connect them with single bonds. That's going to spend 3 bonds. Well, we had to have 4. So where are we going to put our 4th? Well, that means we got to have a multiple bond. Notice they're all S to O bonds. So it doesn't really matter where you put it because in essence, they're all the same thing. So I'm just going to draw it to the bottom one. You could have drawn it to the left or to the right oxygen. It really doesn't matter. They're all fine. So this is what I mean about it's usually not that big of a deal. Just don't put it to a hydrogen or a halogen and you'll be fine. Next, everything's supposed to have an octet. That's what we're doing is drawing octet structures, and they've got to have a full octet to be stable. So that's what we do next is we fill in dots so that all atoms have full octets. So if we had something like HCl, Well, our hydrogen only needs 2, so getting a bond, it's done. You will never, ever, 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 ever draw dots around H's. They are done with their 1 bond. But most other substances are going to need dots. Our chlorine in this case is going to need dots because that single bond, remember, equaled 2 electrons. So right now our hydrogen has 2 because of the single bond, and our chlorine has 2 because of the single bond. Well, that means we need 6 more to get to 8. So I need to draw in 6 dots. And remember, you always draw them as pairs. Always draw your unshared dots, unshared electrons. The dots we're drawing are things aren't involved in bonding, so we often call them unshared pairs. We always draw them as pairs. So really, if I've got 6 electrons, I'm going to draw 3 pairs here. Now, they're all negatively charged regions, and opposites are going to attract each other. Like charges will repel. So all of these are going to repel each other. So what I'm going to do is I'm going to space them out. My first pair, I'm going to draw exactly opposite my bond because that's as far apart as I can get. And then that leaves 2 left sides here. I'm going to draw a pair there and a pair there. And now I've spaced out my electrons. So just always space out your electrons. You're good. The most important thing here is draw them in pairs. So step 4, you fill in your dots until everything gets a full octet. Now step 5 only applies to when we have, oops, had another one I wanted to do here. We had SO3 earlier. So let's look at how that one would be different. Well, first our sulfur has 1, 2, 3, 4 bonds. So the sulfur already has 8. So we don't need to put any dots on the S. But the oxygen with 2 bonds had 4. So that means I need 2 pairs drawn on that one. So whichever oxygen you drew your double bond, you need to add 4 electrons. That's 2 pairs. But my single bonded oxygen, and let me get rid of my blue bonds I drew in there to highlight to make it easier to see. My single bonded oxygens, they only have 2, so they each need 6. So 1 pair, and then just keep spacing out, and my other 2 pair. So that would be what my electron dot looks like for sulfur trioxide. That brings us to step 5. If it was a polyatomic ion, remember we had to fix A if it was an ion and had a charge. We're going to put the whole thing in brackets and write the charge outside to show anybody who's looking at the structure that it has a charge. Otherwise, based on our electron dot drawing, we don't know that it's gained or lost electrons. So this is ammonium, which is NH4+. Just looking at the drawing doesn't tell us it's got to have a positive charge. So we put it in brackets, and we put the positive charge outside, and this is what the ammonium ion would look like. So remember, we can draw polyatomic ions because they're covalently bonded ions. So step 5 only applies when we've got an ion. Now, let's take a look at a couple here. First, we have NH3. Remember, N stands for how many 8s and 2s? In the case of hydrogen, we only need 2. All 9 hydrogens, we need 8. So we have 1 non-hydrogen and 3 hydrogens. That's a total of 14. Available as countervalence electrons. Nitrogen is in the 5th column. Hydrogen is in the 1st. So we have 5 and 3 1s. That's a total of 8. N minus A equals S. So we've got 6 we're sharing. Divide that by 2. We got 3 bonds. So when we draw ammonia, we need to draw ammonia with 3 bonds. So we're going to put an N with 3 bonds coming off of it. Oops. Let me back up here. And then with 3 bonds coming off of it, and each of those bonds needs an H. Now, each hydrogen is fine because it's got 2 dots for each bond. So our hydrogens are all good, but our nitrogen only has 3 bonds. It needs a pair of electrons. So that's what ammonia would look like. Next one, O2, same idea. We have 2 non-hydrogens and 0 hydrogens. That's 16. Oxygen's in the 6th column across the S&P block, so we have 2 6s. That's 12. That means we are going to be sharing 4, which means we have to have 2 bonds. So we draw my O's next to each other. Let's go red this time. And we need to connect them with single first, but we're supposed to have 2, so we have to add another. Didn't have a choice. Now that means each oxygen has 4 electrons right now. Well, they need 8. So I've got to draw 2 pairs here and 2 pairs there. Notice once again, I spaced them out. Next one, we have HCN. We have 2 non-hydrogens and 1 hydrogen for 18. Hydrogen has 1 valence electron. Carbon has 4. Nitrogen has 5. Total of 10. So we've got 8 being shared and 4 bonds. So when we go to draw this, well, remember, the least electronegative thing goes in the middle. Well, notice in the formula it says HCN. Often we write our molecular formulas to help see what the molecule is going to look like. So in this particular case, Carbon turns out to be the least electronegative, so that's going to go in the middle, and that's why it was written that way. Now first we connect with single bonds. I spend 2, I've got to spend 4, so I need to write 2 more bonds. Remember, I can't write them to hydrogen. That's 2 electrons and it's done, so 1 and done for hydrogen. So that means my C and my N must have a triple bond to get my 4. Now I add my dots. Hydrogen's got 2, it's done. Carbon's got 8, because 4 bonds is 8, it's done. Nitrogen has 3 bonds, that's 6. So nitrogen's going to need a pair. And that would be HCN. Now the last one here, C2H4, going through the process. 2 hydrogens, 4 hydrogens is 24. Each carbon has 4, each hydrogen has 1, that's 12. So I'm going to end up with 6 bonds. So when I go to draw this one, I actually have 2 in the middle here, because my least electronegative thing is carbon, so I'm going to put both of them in the middle. And then I'm just going to space out my hydrogens. Now everything needs to be connected by a single bond. So I'm going to connect my 2 carbons first. Those hydrogens, that carbon, those hydrogens, that carbon. And now I add my dots, because that's 6 bonds, so all I have left are dots. Well, carbon each has 4 bonds, that's 8, so that's good. Each hydrogen never needs dots, because 1 bond, it's done. So that would be C2H4.